The table here lists the characteristic X-rays of both plutonium and uranium. As you can see, there are more than one possible X-rays. These different energy X-rays come from the difference in the potential energy between the innermost electron orbit, the K-shell, and the initial position of the electron in the outer shells before it drops to the K-shell. Uranium and plutonium also emit gamma rays, and this table lists the most prominent gamma rays as a function of isotope. Notice that the activity, given in gammas per gram per second, varies wildly, ranging from 10 to the 10th gammas per second per gram for americium-241 to about 25 gammas per second per gram for uranium-238. All of the higher actinides are subject to spontaneous fission to a greater or lesser degree, and they emit fission neutrons when they do. Again, notice the huge range of activities that are possible, from 2.34 times 10 to the 12th neutrons per second per gram of californium-252 to 10 to the minus 8th neutrons per second per gram of thorium-232. Also notice that the neutron multiplicity varies between 1.9 for thorium to 4.6 for californium. As you can see, the neutron multiplicity is generally less for spontaneous fission compared to induced fission, the exceptions being thorium-232 and americium-241. These fission neutrons are produced in a spectrum of energies. We think that the neutrons boil off from the neck connecting the two fission products just as they are fissioning. So the energy given to these neutrons depends on the multiplicity of the neutrons, the final energy of the two different fission products, how much of this energy is passed to the neck as the fission proceeds, breaking into two parts, and half a dozen other things. Here's a graph of the neutron energy spectrum giving the probability of finding a fission neutron at a particular energy. You can see that the most probable energy is around 1 MeV, and essentially no neutrons are created above 20 MeV. There are also almost no fission neutrons created with energies below 10 eV, and the curve rises rather sharply to its maximum starting at about 10 keV. Returning to look at the neutron multiplicity distributions, we see that for induced fission, the multiplicity goes up with increasing Z, so that plutonium has a higher multiplicity than uranium. For spontaneous fission, californium is the only isotope with high enough spontaneous fission rate to make measurements easy. So you can see here that as the mass number increases, so does the neutron multiplicity.